Alright, we're back again. What you're seeing here, this is a 120 volt circuit. These are a dual SCR setup that is used to simulate a Triac. This is an Arduino Uno. Here's my zero crossing detector, and here's a control. And I'm just simply controlling the intensity of a light bulb, as you can see here. Alright, we'll discuss the dual SCR circuit. This is the same circuit that I've used with Triacs and a number of other things. So this discussion is going to be on why I would want to use two SCRs instead of one Triac. And we'll see how that works out. One reason we would use dual SCRs is because each SCR is only on half the time. That means it can handle a lot more power if necessary. In this series of videos, we have discussed a number of electronic circuits related to these solid-state relays, the GN series from Cridom. We've discussed input circuits, current limiters, all kinds of optocouplers. Now we're coming to the output circuit, which is dual back-to-back silicon-controlled rectifiers. If you can look over here, cathode to anode, but notice the gates are not connected. You should have already seen the video with the lamp being controlled by an Arduino. Let's look more closely into the circuits themselves. Alright, here's a snapshot from the video of this setup that I constructed. Here's my intensity control and Arduino Uno, 120 volt AC lamp. Here are my two SCRs, and here is my optocoupler that connects the control signals from Arduino to the high voltage SCRs. Of course, here's a zero crossing detector over here. In another video, I already addressed the issue of optocouplers being connected to SCRs. You have the H11C4 types that have a SCR output, as shown here, or if you use a diode, you can use an MOC 3011, which is a photo Triac, and you'll be utilizing half of it, but it seems to work pretty much the same. Let's note a little bit what you're seeing here, the right and wrong ways to connect Triacs to make Triacs out of SCRs. Let me give you a reason why I would want to do this. This can handle far more power as two separate SCRs as opposed to a single Triac, because each element is only on half the time. Over here, you'll see this is drawn. It's cathode to anode, but a lot of people, and this is all over the web, that they're tying the gates together. Guarantee you, it does not work. I tried it. It stays on all the time. This is the proper way to wire and configure these back-to-back SCRs if you're trying to use them as a high-powered Triac or AC switch. Alright, let's look at our first circuit before I explain to you the current flow in this. I have, of course, two SCRs, and if you look close, it's cathode to anode and cathode to anode. But this time, I'm using two photo SCR optocouplers wired as shown. And yes, you need that 47K resistor that people keep asking about because it controls the sensitivity of the optocoupler SCR gate. Nonetheless, this is how the circuit works. I have a light bulb and I'm using 24 volts AC, even though the video that I showed earlier used 120 volts, works the exact same way. All right, let's look at the current flow. This side of the circuit is on the positive half cycle. Remember, this is AC. This is the negative half cycle. If we follow the current flow here, the anode to the lower SCR is positive. Of course, when I trip on this optocoupler here, a small current will flow through the gate current through the 270 ohm resistor. This SCR will turn on and it will complete the circuit back through the light bulb and the negative. This one will remain off because on this half of this side is negative with respect to its cathode, and thus this SCR will stay turned off. All right, our polarity has now reversed. This side is negative. This side is positive. If we follow our current flow through the lamp, we will find that the anode of the upper SCR is positive with respect to the cathode, and thus when the associated optocoupler is turned on, the SCR will be turned on, and thus for that half cycle the lamp will be turned on. Down here at the bottom though, the lower SCR, the anode is negative with respect to the cathode, so it remains turned off. And so what you've got here is a situation where one SCR is on half the cycle and the other SCR is on the other half of the cycle, and thus the power load is distributed between the two devices. All right, this is the circuit that I happen to be using in the earlier video. Again, I have two SCRs, anode to cathode, and my two gates go off on their own associated components. In this case, I'm using an MOC30XX. I think a MOC3011 is what I was particularly using. That is a photo Triac output. And what happens is these two diodes that's across the what happens here is you've got these diodes across the gate cathode circuit of each SCR. When the appropriate half cycle, okay, let's look at it from the viewpoint of SCR2. This here is going positive with respect to the cathode down here, coming from the optocoupler. It's really coming through, it's positive here, goes through positive, moves through the optocoupler to here. When this is positive here, D2 is reverse biased and remains turned off, and thus it generates a current through the gate cathode circuit, thus turning on the SCR. But up here, the same positive voltage coming in on the cathode up here will assure that this SCR is turned off during that half cycle. When the polarity reverses again, when this goes negative here and positive there, this SCR will be reverse biased and turned off. But this SCR will be forward biased and will be turned on. These diodes are used to block the appropriate half cycle that doesn't turn on. What it does here is it keeps the negative going associated half cycle off the gate. So that's how that works. It is one optocoupler, that's fine, but you can use two, and this gives you an idea of the kind of circuits you can build. This comes right off the manufacturer's spec sheet for the MOC3011 optocouplers. So I hope you enjoyed this and it's useful. Visit my website at www.bristolwatch.com and good luck.